Welcome to another exercise for the workbook statistics. This time I'm going to talk about simple linear regression and how we can determine the coefficients for a regression line. Well, let's have a look at the exercise. Here we have determine the coefficients of a linear regression line that describes the relation between the monthly net income in €1,000 and the average monthly expenditures for garments in euros. Interpret the coefficients of the line and determine furthermore the coefficient of determination r squared. All of this based on this data set. So we're going to use those 5 observations here to actually start with the regression line. Then we can talk about the results and then we can tackle the r squared. So I'm going to copy the table. Then I'm going to first off assign x and y values. Here it's actually important to know what is the dependent, meaning the y variable, what is the independent, meaning the x variable. Here we can assume that net income actually drives expenditures. So x being independent, y being dependent. With this addition, I then add 3 additional rows to the table. In the first row, I'm simply squaring all my x values, so all these 5 values, I'm going to take to the power of 2, giving me these 5 results. And then I'm going to do exactly the same thing for y. So 250 squared, 90 squared, and so forth. That's the second additional row. The final additional row, here I'm going to multiply x and y values. So those two, and so forth. Giving me these 5 values as a result. Then, as an intermediate step, I'm going to simply add up whatever I have here for all of my observations. That's this column here with the sums. And this, as I said, is just intermediate because what I actually need are the averages. So I'm going to divide the sums, this column here, by 5 since I have 5 observations, giving me those 5 averages. That's actually the only thing I need here, those 5 averages. So if you want to leave out the column with the sums, want to leave out those intermediate calculations down here, that's perfectly fine. We are not really needing this. The only thing I need at the end are those 5 values over here. And well, as I said, that's more or less it for the first part. So we can start with our coefficients. I'm just going to copy the table. Then we're going to start with the slope of our regression line, which is here b and follows this formula. So the upper part, that's the covariance. So that's the average of x times y. That's the last one here, the 298.8, minus the average of x times the average of y. So minus 1.98 times 142. That's this. And down here, I have the variance of x, or average of x squared. That's the 4.534 here, minus the average of x, the 1.92 to the power of 2. So I'm going to put those numbers here, giving me an end result of 28.7484. This result, the slope, could be negative, could be positive, can be smaller or larger than 1. So here, this is of any size, so I cannot really control did I do this correctly or not. Just have to trust that this actually makes sense at a certain point. Well, once I have this slope, I can also calculate the intercept. The intercept via this formula. So the average of y, the 142, minus b, which I calculated before, times the average of x, which was the 1.98. This gives me an intercept of 85.0782. Those are actually the two coefficients I need for my regression line. So the regression line as such would read y is equal to 85.0782 plus 28.7484 times x. If I'm going to use this information, I can directly calculate one more row for my table, which is the y hat squared. What's y hat? Well, y hat is the value I get if I insert my x value in the regression line. Or in other words, if I calculate 2.3 times 28.75 plus 85. Then, that was the y hat, take it to the power of 2. Giving me here, for example, 22,861 point something. Then I'm going to do this for the other x values. So I'm going to go with 1.7 times 28.75 plus 85, 0.8 times 28.75 plus 85, 1.9 times this plus this, 3.2 times this plus this, and all of the results squared at the end, giving me those 5 values. Here again, I'm going to calculate the average. Why did I calculate the average? Because I'm going to need this for the coefficient of determination, which I still have to calculate. For this coefficient of determination, I actually have two possibilities which I could go about. The first is a more general version. That's what we're going to do here. Or if I have a simple linear regression, I could also calculate Pearson's correlation coefficient for x and y and simply take this to the power of 2. So for most, this is the more easier version. Here we're going to go with the slightly more complex but general version, which will also work for multiple linear regression, which the Pearson correlation won't anymore. So let's continue with this part. So I'm going to copy the table from before, because all the information we need for the coefficient of determination already is in this expanded table, because that's our formula here for the coefficient of determination. This is just the value for which we included this last row. So that's y hat squared, the average thereof, 20,671. Then we have here y, the average, that's 142 to the power of 2. And here y squared, the average, that's the 23,500. So if we insert this, we get as a result 0.152. Well, from a calculation perspective, this concludes this exercise, but we still should say some words on what the numbers we just calculated actually mean. And well, on the slide before, when we calculated the regression line, we saw that we had roughly 28 for a slope. So this means for every x more, y increases by this amount. Well, x, the net income, was measured in 1,000 euros. So for every 1,000 euro I earn more, I spend on average 28 point something euros more on fashion. That was the slope telling us. Then we had the intercept with 85. The intercept means if the net income, if x is 0, that's the value for y. So if I do not earn anything, I spend on average 85 euros for fashion. That's how I can interpret the linear regression line. Then I have the coefficient of determination. This tells us how much of the variance of the y can be explained via the X variable or via the general model. So here it's 15.2%. Well, that's not bad, but that's also not perfect. So we could make different threshold values here. And then one of the threshold values would be either 1%. If it's below 1%, it's negligible. We don't need it at all. The next one would be roughly 10%. So something between 1 and 10%. That's okay. That's not perfect, but it could be better. Finally, we have 10% to 25%. That's medium strong relation. So that's what we have here. So it's a good result, but it could be better. And everything larger than 25%, that's actually a strong relation. Well, here this is at least decently sized. So we can explain a decent share of fashion expenditures, even though we cannot explain everything about it. Well, that then concludes this exercise, which I hope you enjoyed. I say goodbye and see you next time.